yeah, first, there's some of these problems that are just taught in a hurry. So, but today, let's go back to these kind of dynamics. I think, first of all, it's a very kind of easy dynamic because you know that it's a kind of linear kind of equation, or linear ODE. It's like linear ODE, but actually you can see that it's in the frequency domain. So let's look at this P here. So this P refers to an empirical distribution, which in general is a kind of a summation of deltas because we only sample at discrete points, right? And let's think about the case where there's no this P here. There's no this empirical distribution. Therefore, this H is just a Fourier transform of the function we care about, right? It's a function of the neural network. And therefore, what we can see, suppose this F, there's a no P here. So this F is a target function. And then this H is the function, say, neural network function. And then it tells you, okay, the evolution of the neural network function in the Fourier space, it's a kind of actually, the dynamics of this neural network function is decoupled in the Fourier space, right? You can see each of these Fourier modes, for example, given certain cases, you can see their evolution are kind of independent. It means that they have no coupling between different frequencies. Then what happens is that each of these terms, for example, H, initially probably it's a kind of zero function. Therefore, all these frequencies are zero. But later, since there's this term, arrow term, that drives the Fourier transform of the H to the Fourier transform of this target function. And later, all these components in the Fourier domain will converge to the corresponding kind of Fourier components in the target. So, and all independently. It's just, yeah, please. H and HP is different because you see, here's a notation. So if I put this small p here, that means some function times this p. This p is generally, for example, here, it tells you only the information at certain empirical samples are observed. Therefore, there's some delta here that marks that fact. So without this P, so you can see it's a very simple dynamics, which means each component in the Fourier domain converges to that component of the target exponentially. And the decaying factor is determined by this prefactor. And it's decaying in a power law manner in the Fourier domain. That means, okay, the lower frequency part, all of these components will converge to that Fourier component of the target. However, it's just the lower frequencies converges faster, right? The higher frequency converges in more slowly. However, what's really interesting is not about that. It's about when we only have the observation at finite samples, right? That means what we can observe about the target is only at these training samples. Nowhere else we know the information of the target. And also, in this arrow term, we only care about whether the neural network output function evaluated at these training samples. We only care whether they match that of the target. Therefore, so both HP and FP kind of only care about the information of these functions at finite points. And then, so with this kind of driving terms, what we can see is that there could be some aliasing effect. For example, if like this F, the target is kind of a high frequency oscillation. However, we only observe these target function at these kind of sparse kind of points. Therefore, you can see aliasing could happen in a sense that H not necessarily equal to P, right? For example, if H here is this kind of yellow line, still you can see HP Fourier transform is equal to the FP Fourier transform, because at these training samples, these two functions, this yellow line and this target function, aligns perfectly. Therefore, these arrow terms will become 0. So that means, the aliasing means, okay, if your data is not kind of dense enough, then a lower frequency Fourier mode can align exactly with a higher frequency Fourier mode. Therefore, there's no way to distinguish, so whether it's a kind of higher frequency mode, right? Both of them is able to explain these observations on these sparse grids. And then we ask, okay, since we can use lower frequency modes to explain things, and we can also use higher frequency modes or much higher frequency modes to explain this training data, what kind of solution will neural network learn, right? But now you see, this dynamics tells you, okay, we prioritize over the lower frequency part. That means although the higher frequency modes will also grow, and also the lower frequency part will grow in order to fit all these kind of training data. But because the lower frequency modes will evolve faster, therefore, when already lower frequency modes leads you to almost 0 training error, then the training stops. The higher frequency mode do not really have time to evolve to a sufficient amplitude. And then what you should expect is your neural network learns this kind of more like this kind of orange curve, right? And that is behavior of this dynamics. And so this dynamic says among all these H that matches with this target at this empirical distribution, at these samples, these dynamics will prioritize over the interpolations that is dominated by lower frequency part. And then you can tune the activation function to adjust the priority between the higher frequencies and between the lower frequencies and the higher frequency. Yeah. And you can choose, for example, if you choose Tang here, then what you observe here is a exponentially decay term in the frequency domain. That means a much lower priority into the higher frequency part. Okay, that's the general behavior of this linear frequency principal dynamics. And, but I must emphasize that this is not a realistic kind of setup, because it has very strong assumptions on the, for example, initialization, and there's a specific regime. Only in that regime we can write down this formulation. But what's good about this kind of limited setup is that we can write down, or we can prove the equivalence between this kind of learning dynamics, right, with this static problem. The static problem says, okay, since the laws tell you on every training samples, you must interpolate the data. It must equal to y, right? But this dynamics will, from all these global minimizers, from all these interpolations, choose an interpolation that minimizes this kind of, we call FP norm. So this FP norm, there's an inverse -1 sign here that tells you, okay, this exponent is increasing the Fourier domain. That means there's a higher and higher penalty over the higher frequencies regarding these interpolations. Okay, so this linear frequency dynamics, as I've told, in a very specific case, you can rewrite this FP norm into this, the original domain, into the spatial domain, where you get this, for example, the minimizing the square of the derivative, or minimizing the square of the second derivative, which correspondingly give you linear spline or cubic spline. What you can see is that this Cassi to the fourth is a kind of a faster decaying kind of exponent, right, or faster decaying rate. That means a higher regularity, right? The higher regularity, therefore, since you require a higher regularity, that means this inverse term increases faster, or the penalty increases faster over the when the frequency increases, then it leads you to a more smooth spline of the problem. Okay, and how we tune the network so that it can behave differently, or it can kind of become more like linear or become more like cubic. What we do is just tune these initial variance. So all these things, this R square, which in this bracket means the mean value of this R square at the initial training. And then just by tuning the scale of these initial parameters, then we can tune the network to a regime where it works like a linear spline, or to a regime where it works like a cubic spline. Okay, and in this limited setup, you have a full control of how the neural network learns different kind of interpolations. So that's something good about these simple dynamics. And also in a high-dimensional space, if like your target is it's a d-dimensional, and then the decay regarding to the ReLU activation is actually this. There's a component. There's an exponent d here. The d here means in a high-dimensional space. So this decay is actually faster. So why there's a kind of faster decay? The reason is as follows: the higher frequency modes in the Fourier space are actually occupies a larger volume, in a sense that, for example, the base frequency is always 0, right? But let's see the frequency of 10. That means have the constraint that the Fourier vector or the frequency vector has the L2 norm of 10. So that's a sphere, right? The sphere in a higher dimensional space, the spheres like occupies a larger volume relative to, the higher frequency will occupy a little bit larger volume than the inside part. Okay, that's why we have these D factors here. Okay, and then, so there's this is the formal theorems. But now we use this equivalence relation to look at this, the initialization impact. You can see if I have some initial output function, the initial output function, for example, since I randomly initialize all the parameters, initially there's an output function. This output function is not relevant to the output, to the target, right? However, right, it may have some, for example, particularly if you initialize with large variance, it could be an oscillatory pattern. So if initially you have some, for example, highly oscillatory pattern inside, then actually it tells you, okay, so we still has a lower frequency bias. But this lower frequency is only about the difference between the initialization and the final interpolation. It tells you, okay, so the difference between the initial output and the final function, this difference should be dominated by the lower frequency, because that's what is this term penalized. But the initial high frequency part is actually not penalized. So that is the information. So this difference must be dominated by lower frequency. But if the initial part, there's a high frequency part, so that will be left to your interpolation. So that's a very important information. Therefore, a very easy way to overfit the system is to initialize a network so that the initial output is highly oscillatory or contains very strong oscillatory patterns. And then, throughout the training, I tell you, based on these dynamics, the difference is dominated by low frequency. But the final output is then the summation of the initial pattern together with that lower frequency dominated kind of a difference. Therefore, there will still be higher frequency part left in your interpolation. So that is one part of the initialization impact. Okay, and now let's go to this kind of a little bit more kind of advanced results, which is regarding the generalization error. Since it's a linear dynamics and there's a very clean static form where this FP norm gives you how the neural network prioritizes over all these possible interpolations. And then we can derive, based on the complexity, Rademacher complexity, and we can estimate the generalization error, where a key term that here is this FP norm of this target function. Here, this is a priori generalization error bound. The a priori means I'm allowed to use the information of the exact target to estimate the error or generalization error of my algorithm. And then what you can show is that the FP norm of the empirically learned function will never be greater than the FP norm of the target function. Because it's like following, since you minimize over this FP norm, and if there's no sufficient data, and then they will always choose an interpolation that has a lower FP norm. It is with so many data that you actually force the network to learn the target or the FP norm exactly matches target. Otherwise, there's always exists interpolation with a lower FP norm than your target. Therefore, so all your fitting, what you know about fitting is that its FP norm must be lower or equal to your target, the FP norm of your target. Then this theorem says, okay, what you need to do is just to measure the Rademacher complexity of all the functions FP norm less equal to the FP norm of your target. So that's everything you need to do. Then you measure the complexity of the function space you are searching, right? And then you obtain this error bound. Oh, the LH is actually the we call population loss. So this loss is evaluated over through the, you see, this is called population risk. This population. So we defined it using an integral. So essentially, so we have like the empirical loss is like f theta yi. So it's like this. So maybe let's just write down the L2. That is an empirical risk. The population risk is an integral over this minus, say, this f star. This is a target function. So this is actually f star xi. So there's no xi here. It's x. Let me write just in a kind of strong form, for example, rho x. Then it's there's a distribution. Because here I already have this rho here, so just put an integral over the whole dimension. And then this rho x is the distribution of these samples. And this integral is called population loss. That's right, actually. That's right. So you define yeah. Yeah. That's right. Yeah. So here it's about this problem, this static problem, no initialization. Exactly. Training sample. Yeah. The Monte Carlo rate. Yeah, that's right. Yeah, this is a logarithm. And you can see in which sense from this kind of a bound, the key information is that suppose we have two functions. For example, for example, we can compare this, for example, sine 100x. That is one target, and another is sine x. Consider which one has larger kind of generalization error regarding that kind of a simple model, right? And then you can see the L infinity norm is actually the same. However, the FP norm, there's a huge difference, right? And in the FP norm, what we need to do is to do the Fourier transform and see the frequency. Depending on the different frequency, it has different penalties. So you can see that because this is there's a 100 like, so this in terms of FP norm, you can see, for example, if we consider the FP norm, that looks like, for example, there's a Casey square. And then it means this function, the FP norm of this function, gamma, and compared to this kind of FP norm of this gamma, the relation is about 10 to the fourth, right? Because the frequency difference is 100, right? And then because there's a Casey square, right, this kind of penalty. Therefore, since this is kind of 100 times, therefore 100 square is a 10 to the fourth. The FP norm has huge difference between these two different targets, right? And if this frequency is higher, then the FP norm of this target will become even higher, right? And yeah, and if you choose this kind of FP norm, like say to the fourth, then the difference between higher frequency and lower frequency can be even larger. So that tells you, okay, from these results, you can see, so if your target is high frequency, and then you fix the number of samples, for example, n samples. If your target becomes higher frequency, has higher frequency components, and then the generalization error becomes large. Otherwise, it's lower frequency, then its generalization error is relatively low. But let me tell you, don't really trust this inequality quantitatively. If you say, okay, since I derived this bound, I'll try to see whether, because all these things I can compute exactly right, there's a quantitative result, right? Don't trust that quantitatively. Yeah, generally this bound can be like, if there's a 10 times difference, it's a very, very good, right? But the quantitative, the qualitative predictions, that's something we really care about. For example, this kind of bound tells you, okay, the higher frequency your target is, the higher generalization error you should expect. That qualitative predictions is something that we really try to extract from this kind of bound. And this matches the kind of result or kind of empirical observation we have. And now, after all these understandings of the frequency principle, so we have a bit more understandings, or at least we are able to have certain level of answer to the Liu-Breman's problem. For example, why don't heavily parameterize the neural network overfit the data? We can say, okay, because it's prioritized over the lower frequencies, right? If your target is indeed, most of the target are indeed dominated by lower frequencies. Therefore, it does not really have the tendency to overfit. And the last problem is about when should one stop the backpropagation and use the current parameters. I say, okay, so since we know that there are some higher frequency things which are noise in your data, and then I want to stop in a part where the neural network does not really captures the higher frequency noise, but already captures the information, the lower frequency information in your data. And there's a standard protocol called early stopping, where you use validation set to stop. Okay. And yeah, all these other two actually, so it's still there's more mysteries. We will leave for example, the condensation phenomenon to actually have a better answer. Okay, and now if you go back to this kind of observation, which it was done in 2017, okay, we use neural networks of over 1,000 parameters, and we train the neural network on these 5, to interpolate these 5 training data. You can see all of these interpolations are kind of dominated by lower frequencies. Yeah, and now you understand why that could happen. And you can also understand how you can actually use a high frequency fitting to the problem. What you do is just initialize the network so that the initial output is a high frequency. And then you will be doomed to overfit the problem. Okay, and the general picture for this generalization puzzle from the understanding of the frequency principle is that there's a huge parameter space, however, with certain number of training data, but not enough, not as many as the number of parameters. So there's still a very high dimensional manifold of the global minima. And among them, if you have some unbiased initialization, means the initial output is 0, for example. That means there's no bias at all, right? No high frequency components. And then you can see that the neural network will give you a low frequency dominated interpolation. And so that marks this kind of a little red circle where, like, as long as it's dominated by a lower frequency part, generally they are kind of have certain level of generalization guarantee. Okay, but there's more to be discovered, as in the phenomena of condensation. Okay, there are some of these references. I mainly talk about this the first 4 papers, but there are kind of more details I don't really have time to talk about. And there are some problems you can try. I mean, if you are able to answer all these 5 questions, that not only means you have a good understanding of the frequency principle, but also means the neural networks are no longer that black box to you. Okay, the first problem is, how can neural networks be prevented from overfitting to noise in the training data? The second is, how can the convergence towards high frequency components of the target function be improved during training? In many problems do have high frequency components. What kind of a method we can use to improve that? And third is it possible to design a model that prioritizes fitting higher frequency components before low frequency ones, right? So that's a really interesting one. And the fourth is what characteristics of a target function or data set makes it difficult for a deep neural network to generalize. That is regarding the limitation, because we are used to, okay, the neural network functions are so powerful, right? But what kind of training data that the neural network can never really do a good job, right? So that's a question you should have some understanding. And what methods or conditions can be employed to induce deep neural networks to overfit the training data? That is about the initialization I mentioned to you. Output function is kind of weird, and you can try to see if it's destined to kind of overfit. And that is about the frequency principle part. And now let's go to here. Let me before I go to the later topic. So probably let's look at a very interesting observation that, as I've told you, it's easy to overfit the problem, right? So what we do here is like there are So what I do, I use a neural network to train on these red training data points. They are very dense, but there are intervals. Okay, so the blue line is the initial output function. How I induce this initial output function, what I do is simple. For all the parameters, I initialize from a Gaussian distribution with the standard deviation of 10. Standard deviation of 10. And then this is how it looks initially. And after training, so this is a graph I plot only at these training data points. You can see the on these training data points, it works reasonably well because I have data. But if I evaluate on a much kind of denser grids, and then you can see that these there are some kind of high frequency oscillation between the training data points. Right? And if you initialize with a very small variance, and that is what you see, they are not only good on the training data, but also good on the testing data. And this phenomenon tells you, okay, so the neural network is actually very easy to use neural network. Yeah, this is actually use a sigmoid function. Yeah, but because we have the understanding that all these high frequencies are inherited from the initialization, whatever activation you use, just make sure you have higher frequencies or enough energy on the higher frequency part on the initialization. Okay, so is there any method that we, on the one side, we use a very large kind of initial variance, but on the other side, they don't behave, they don't fit in a crazy manner. Is it possible? The answer is yes. Let me tell you how to do that. So there's this trick called anti-symmetrical initialization trick. But let me tell you, it's not a trick that you should really try in practice. Why? Because in practice, you just use a smaller variance at initial stage. But here, later you will see that if you really want to see the effect of a larger initial variance, but at the same time you want to eliminate the kind of a bias over the initial output function. And then this trick is actually helpful. It eliminates the bias from the initial output function. So what we do is like whenever we have a neuron, we initialize this part in a kind of normal way. However, after initialization, we kind of duplicate this network into this, we kind of have a duplication. So we have this both part, and the output weight are kind of work in a way that these are like a 2 to square root 2 over 2. The one side is square root 2 over 2 over for the initial outputs, and the other part is a minus square root 2 over 2. And therefore, these both parts at initialization will cancel to one another, therefore leading to a fact that after this anti-symmetrical initialization trick, where you're doubling the neural network, then the initial output function will stay 0, despite all these variants of the theta are actually very large. And with this trick, you can use very large initial variance, but don't worry about severe overfitting. Yeah, so all these parameters are duplicated exactly the same as this black one. So I first initialize this black one from drawing from some random distribution. And then I duplicate all these weights to the red one. It's only at the last layer I kind of have a minus sign. And then these two parts will cancel to one another, leading to a zero output function at the initial training. Both together. But these two will cancel to one another. At the initial bias, because this part easily have some like oscillatory initial output. But having both sides will make sure the impact of initial output canceling to one another. So this trick, so it's not practical, but it's very good for theoretical analysis, and later you will know. And if you really adopt this trick, then you are allowed to use a higher kind of a variance at initialization without worrying about severe overfitting. And okay, I will just end here. And now let's go to these I mentioned to you a little bit during Okay, again, the general illustration of the there's a general illustration of the condensation. But just there's something I want to mention to you, that the frequency principle, remember how we observe the frequency principle. We observe the trajectory of the output function throughout the training, right? But does output function gives you all the information about the training trajectory? Answer is no, right? So the output function, so we did not run the gradient flow or gradient descent in the function space. What we are doing is we run the gradient descent in the parameter space, right? And the function space trajectory is actually induced by a trajectory in the parameter space, right? Therefore, so looking at this problem from the function space, it's like looking at something in a fog, right? You see a little bit about the coarse-grained structure, about what's there, right? But you can't really see clearly the details. Therefore, the frequency principle part, like after working on frequency principle for like 2 to 3 years, we kind of have the feeling that it's about that, right? In certain regime, which is actually not so realistic, we can have quantitative understanding. But in general, we're not able to use frequency principle to a quantitative level to understand the nonlinear training that we really observe during the training of neural network, or the neural network really operate on. Okay. And then now it's time to go to the trajectory in the parameter space to see what really happens during the training, during the evolution of all these parameters. And that's how we observe the phenomena of condensation. So initially, all these weights are kind of drawn from a random distribution. And after training, some weird thing could happen, or some unexpected thing could happen, that different neurons, their input weights can be very similar to one another. Generally, it's not possible that they become exactly the same, but so they can become very similar. And whenever this neuron, their input weights become similar, that means the neural network is effectively a kind of a smaller network where you can combine these weights from the same neuron, and you can combine different neurons to one neuron. So in a condensed state, the large neural network is effectively a much smaller network. So that is the general illustration of the condensation. And then now let's look at the real phenomenon. So first of all, the condensation, how to observe condensation. We should start from some small variance of sigma. If we start from relatively large variance, we can often get more close to the neural tangent kernel regime where the dynamics becomes more linear. However, that is not the regime we are actually interested in. If you want to find a regime where the neural network learns in a nonlinear manner, so the easy choice is just to start with relatively small initial variance. And then, whenever you do that, this trajectory is what you can easily observe, where the neural network could stagnate for like quite some time and then drops. And I can see in many problems, what you can observe is that if you start from some relatively large sigma, the training error will drop fast, right? And even in the NTK region, we can prove linear convergence. That means we should observe a training trajectory that decreases very fast. However, as long as you gradually tune down the initial variance, then it could stay in some plateau for quite some time. So why is that? It is because if you set all these A, W, and B to 0, you arrive at a saddle point, or at least a critical point, because there's not necessarily kind of the negative Heisen eigenvalue. Okay, and it is because so, if this sigma becomes smaller and smaller, you stagnate for quite some time. Okay, and actually, I mean, this morning I see the experiment from Ziqian, and I see that in some experiment, it stagnates at a certain level at the initial stage for quite some time. That probably means in that problem, your initialization is actually small. And if you want to accelerate the kind of convergence, and then probably you should tune up these initial sigma if what you care is to get a lower training error. Then that could help. Yeah. Small sigma. And particularly if you tune the sigma to 0, everyone is 0, then you arrive at a critical point. The reason is, in the chain rule, this AJ, the further you are away from the critical point. And then it means that the further away you are from that critical point, that means that initial gradient could be large. If you are closer to that, the initial gradient can be very kind of small. That is what you should expect. And there's always ways to accelerate or to let it stay for a longer time. Yeah, there's always means to tune just through tuning the initial variance. Okay, and then if you observe this kind of training behavior, the most easy thing you do is, for example, you just stop at 1,000 epoch and you say, okay, my problem stop at a local minima, right? But actually, if you wait for a longer time, it will go down. So don't conclude that your architecture kind of stuck at a local minima if you just stop at 1,000 epochs, right? You should train longer. But there's always means to accelerate this process. For example, you use Adam, like that can help escape these kind of plateaus faster. And also you can increase the magnitude of this initial variance. That also helps your training. Okay. And then, so we are in a setup with this two-layer ReLU neural network with this m different neurons, means m different particles in this graph. And you may remember that I always ask you to experience the whole trajectory without any bias, right? How is it possible? Because you can see that the dimensionality of this theta can actually is much more than three-dimensional. Therefore, if we want to observe the behavior, we must choose some more clever method. For example, here we adopt a kind of particle viewpoint in a sense that we observe that different neurons are kind of in an equal status, right? They are just evolved differently depending on their initialization. That is something you can expect. And therefore, you can regard each neuron as a kind of a different particle. And then you can visualize the evolution of all these small m number of particles in its space. Of course, you can see this space seems to be three-dimensional, but remember that ReLU is a homogeneous activation. Therefore, we can reduce this, the information of these neurons from 3 dimension to 2, where the 1 dimension is this is a kind of angle where the x-axis is the W, which is this this W, and the y-axis is the B. And this direction tells you, okay, where the discontinuity happens for that ReLU function. And then the amplitude, for example, this capital AJ, is a product of the absolute value of this AJ together with the L2 norm of this W and B. So this tells you the amplitude of that feature. And then you can plot with this kind of 2 coefficients, and then you can plot the whole training trajectory throughout the training. And then this is a trajectory you can observe. And these blue lines are the trajectory, the history trajectories of different neurons. Yeah. Oh, you, yeah. Yeah. Yeah, that's right. Yeah, so these two determines where this kind of discontinuity derivative happens. That's right. That's right. So therefore, this angle, if the neurons are in different angles, that means they are accounting for different, for example, here, you can see discontinuities at, for example, here, here, and here. For different different part, that means you should have a neuron at a different angle to account for example, a discontinuity at a different location. Yeah. And definitely, you see, for this kind of training data, you should have like corners at a variety of places. And kind of a one transition is not enough. And then, so if we look at all these things closely, that first we initialize from somewhere around 0. So that is because we use small initialization. So all these amplitude are kind of around 0. But all these angles have neurons. Kind of initialize these angles randomly. However, throughout the training at the initial phase, you can see that lots of different neurons from different angles, they all concentrate in one angle. And at this stage, when they concentrate, they can also shift their angles to a different place. That means the kind of discontinuity, the transition part, there's a shift. And then, because kind of one transition is not enough to capture the training data, and then grows out another group. And the same, here, there's one more group emerged from the center, and also one group can be separated into 2 groups. And there are different ways that the network are kind of become more and more complicated. For example, in this stage, so the output function is effectively kind of 4 ReLU function. And at the next stage, because there's a further splitting, and now the whole neural network, though with like 100 neuron, but effectively it's a kind of 5 different ReLU. And where it stops in a configuration where 1, 2, 3, 4, 5 different groups at the epoch of 100,000. And then you look at the output function when it stops. Okay, 1, 2, 3, 4, 5. 5 different corners. That is because though there have so many different ReLUs, but finally they condense only at 5 different kind of angles, 5 different kind of these corners. Okay, so that is what you can observe. So you experience that, right? I showed it clearly. You use your eyes and you feel, okay, there must be some reasons, or there must be a very important kind of laws that underlies all this phenomenon. So you first have this feeling. Yeah, but you can also see this behavior is very difficult to characterize. In a sense, it's highly nonlinear, right? It's far beyond linear. And then if you look at this training trajectory, you can see that this training behavior marks the fact that the training is in a highly non-convex landscape. So without things, you can see it can stagnate at some critical points. That fact itself means it experiences like a highly non-convex landscape. Therefore, both from the optimization viewpoint or from this dynamical system viewpoint, this nonlinearity or non-convexity leads to huge difficulties in analyzing this phenomenon. Therefore, actually, I myself observed this phenomenon in a very simple, like 2 neuron systems in 2018. However, it's only at like 2020. So I start to know how to write the first paper. For many years, I first worked with my colleague Zhiqing Xu on the frequency principle. And however, it is not until like 2020 I realized how to really make a first step. Okay, and now, so let's look at the generality of this condensation phenomenon. So these things we can visualize in the 2D, right? It is because this is a 1D fitting and there's only like 2 dimensions for its features. Therefore, we can visualize everything. However, in application, we care about this, for example, MNIST data. The input space is 784 dimensions. Like, how do you see the neurons evolve in that very high dimensional space? It's not possible. But as I've told you, since we observe very, very clear patterns during the training of lower dimensional problem, then in the high dimensional problems, we know what kind of quantity we should use to kind of observe this kind of condensation there. So what we do is we use this cosine similarity. So the cosine similarity just is used to quantify the angle between different kind of feature vectors. And initially, for example, if in a high dimensional space, you initialize all the weights randomly, then based on this the theory from this random kind of, I don't know how this view course, it's related to the statistics of the random vectors in a high dimensional space. You can see initially they are almost orthogonal to one another. If you randomly draw, for example, 1,000 different random vectors from 1,000 space, from a 1,000-dimensional Gaussian distribution, and then they are most likely almost orthogonal to one another. That is what you observe here. You can see that these different feature vectors, they are almost orthogonal to one another. However, throughout the training, when you actually train the neural network, okay, you can see with condensation, it stagnates a bit and then goes down, and after a while, the training error goes to very, very low, and the testing error, the training error goes to almost 100%. You always need to make sure that. And then you look at the testing error and the testing accuracy. The testing accuracy is also very good. And then we look at the parameters, and we compute these cosine similarity for all different pairs of these neurons regarding their input vectors. And then that is what you see. Of course, we rearrange this, the index of these neurons. Therefore, you can see approximately 2 clusters. It's not necessary that it's just the neuron with the index from 0 to 15 that should be together, right? There's no reason. Actually, it's quite random, but we can kind of reorder this pattern to see, okay, there are a group of neurons, their directions are similar. And there's another group that are also similar to one another, right? And these 2 groups actually are opposite to one another because you see a -1 sign, right? Means, yeah, please. Yeah, it's all these colors is this index. But just this index is a little bit different from this index. Yeah, because there's no reason 1 and 2 must be similar. Therefore, after training, you can see this tells you, okay, condensation happened. Much more condensed than, or much more aligned than the initial. Okay, and transformer. Okay, now we are talking about transformer. So in research of transformer, like people many times kind of start a do research on transformer regarding transformer as a completely new stuff, right? However, what I can tell you that the condensation which we observe in this very kind of a simple neural network, for example, 2-layer network, right, fully connected network, and it happens for this convolutional neural network, we can observe that clearly. And also we can observe condensation in transformer clearly. And how we do is we can initialize all these parameters in a transformer with different variance. And then, as I've told you, that smaller initial variance leads to more stronger nonlinear training dynamics. And that nonlinearity, it is with that nonlinearity that condensation could have a room. And then we initialize this transformer with a relatively simple, more synthetic data. And what we observe is that you can see, if we look at this WQ, it's a different kind of rows, and we look at their cosine similarity, most of them are actually kind of quite aligned. However, if we initialize the network, all these WQ and WK with a larger variance, and this is what you see. So these different rows are actually more independent or pointing towards very different directions. And however, if you use some intermediate kind of variance, that is what you should observe. There's a kind of a mild level of condensation, but not so clustered. So that is what you can observe. Still, you can see, no matter it is like 2-layer fully connected network, or convolutional neural network, or transformer, or later times some new neural networks, right? You should expect condensation, depending on the scale of initialization. So it's a quite general phenomenon you can easily observe. Okay, and you can also observe on this WK or this WV or WO. Yeah, and you should expect all of these have, you can observe how strong they are, they have condensation just by observing this cosine similarity. And you will have a kind of very good intuition about how strong this condensation could happen. If that is not strong enough, what you do is you tune the initial variance to a smaller value and re-observe these things. Yeah, so it's random. So, but what can be said is that, first of all, they are not necessarily exactly the same number. No. Okay. But it's just approximately. The reason is there are two opposite directions that could be stable for a certain while. And depending on whether you are close to one or another, these neurons choose one direction over another. Therefore, if we kind of initially they are more balanced around different, then it's approximately like half and half. But it's kind of a random thing. So it depends on the problem. You're right. Okay. And everything I told you actually, so it's we did far more experiment. Therefore, I can answer all of these different questions because I did far more experiment, and we can observe these different things. Yeah. And so I also recommend whatever problem you have, you can try to observe this or try to replicate this kind of phenomenon. Then you will have a better understanding about what are the key factors that determine different things. But now these things, I think we have a reasonably good understanding. Okay. And I think probably we should stop. I think we can start now. Now, since you see this phenomenon, and it's a time to talk about our first piece of result about condensation. It's about the regime of condensation. I'm not sure how many of you have heard the kind of notion of dynamical regime. Anyone like heard of this notion like dynamical regime of? Probably no. I probably explain a little bit about the dynamical regime. That, for example, you know this Lorentz system, right? It can have this chaotic behavior, and then by tuning certain kind of parameters, right, it may not exhibit chaotic behavior. And then through tuning these hyperparameters to a certain level, this network works in a chaotic regime. And if you tune it to another kind of value, and it is a non-chaotic regime, we call it like the dynamical regime. So in our brain, there's also this kind of notion, because I'm from the background of computational neuroscience. There's this dynamical regime, so it's very important. For example, so our, for example, if we consider this epilepsis, and then what happens is that this different group of neurons, they synchronize in an unnecessary way, or have very strong kind of synchronization. Therefore, the people just, okay, lose consciousness, right? This is kind of an abnormal dynamical regime, right? And how to actually put the system back to a normal regime where this kind of a strong synchronization does not happen, that is the key to the kind of intervention or kind of try to help these people with this epilepsies. So that is a notion of dynamical regime. Once the system enters into a certain kind of regime, it exhibits a particular kind of a set of patterns, right? And then if not, it behaves in a different way. Yeah, for neural networks, I've told you about there's a kind of neural tangent kernel regime. What happens is that in certain limit, the theta infinity is very, very close to theta 0, right? So that is all you need to know about the neural tangent kernel regime. So it means that the network almost does not change that much, but it is already capable to fit all the training data. Okay, that is the neural tangent kernel regime. Definitely in that regime, because we already know that regime in 2018, we know that regime. And we know in that regime there's no condensation. Therefore, we know that, okay, it is not a phenomenon you always observe, right? But when you should expect strong condensation and when not. And that is problem left. Okay, so how to really understand this problem is there's a basic setup is this two-layer neural network. So of course, this two-layer is kind of a starting point, right? It simplifies things. And also at that time, 2018, there's another kind of breakthrough that is regarding the mean field limit, right? And let me tell you about what is the neural tangent kernel regime. There's one way to induce a neural tangent kernel regime or neural tangent kernel kind of a behavior, means it's a lazy training. How you do that? So for all these kind of A, W, you initialize with some order 1 kind of value. For example, this beta 1 and this beta 2, they're kind of order 1 stuff. And then what you do is to tune this alpha. You make this alpha square root m. Yeah, 1 over square root m, put these prefactors here. So what does this 1 over square root m mean? You can see that it is a kind of stochastic average. Means that if you have a bunch of random variables, how to average them so that at the limit they do not vanish. So it is 1 over square root m, right? You know from this central limit theorem. You know that is the correct way to do the scaling so that the information does not vanish, okay? And that is how people arrive at this neural tangent kernel limit, just using this alpha equal to square root m. But there's another limit that is also used for the derivation of the mean field limit. What is the mean field limit? It's a 1 over m, right? Why 1 over m? In particle systems, 1 over m gives you a density, right? It is using the scaling of 1 over m, you got a density regarding these particles, okay? And at 2018, people already know there are two kinds of limit we can take. One is alpha equals to square root m, the other is m. And these two scaling leads to different consequence. For example, in the neural kernel regime, at the limit, the network is linear. However, for this mean field PDE, it's nonlinear. It's a gradient flow under the Wasserstein metric, and it's strongly nonlinear. And then, let me ask the following question. Which scaling is actually correct, right? One is nonlinear and one is linear, and which one is a correct scaling for the system? Okay, at that time, I think no one actually knows the answer. But I realized that because I observed in this kind of experiment that I actually can tune things arbitrarily as I want. For example, I'm not necessarily constrained by this m to square root m or m. I can also use, for example, m to the power of like 1/4 or m to the power 2. I can use arbitrary one as I want. And then what I do, I observe what's the behavior of the neural network, right? And then what I realize is that because I already understand the condensation, I ask how to tune this, for example, this alpha, right? What kind of the power law relation with this m regarding this alpha can give me condensation? And what kind of setup does not give me condensation? For example, square root m will never give me condensation. Probably like m here could give me a little bit condensation because we know it's nonlinear. And for example, m to the power 2, then what happened there? Okay, people don't know that. And then I also realized that the initialization is important. Like we can also tune this, the standard deviation or the variance of this alpha, of this A and the W. We can also tune that. How people tune that? Generally, they tune them in relation to the width of the network. And therefore, they also have a power law relation with the width of the neural network. And then I ask the following question. So for the alpha, beta 1, and the beta 2, they are allowed to tune into different power law relation with its width. Then, under different kind of power law relation, if I take the infinite width limit, like when condensation could happen, right? Which regime, like which limit actually gives me condensation? Okay, and all these setups, for example, these laws, empirical laws, minimization, or these gradient flows are just normal. There's no much I should emphasize, and there's an infinite width limit. So therefore, it's always an over-parameterized setup, right? Because at the infinite width limit, we have infinite many parameters, right? And it's always an over-parameterized setup. Okay, let's see what are the kind of existing choices of these three different kind of factors in relation to the width. So here I list, for example, LeQueen initialization, He initialization, Bavaria initialization. I mentioned to you that neural networks are actually so easy to overfit. You must have some proper or kind of common initialization scheme. If you follow that scheme, then your training, there's certain kind of empirical guarantee that you get some good result. And then LeQueen, He, or Xavier, these are initializations that people use in practice. These are called common initialization techniques. And that is a scaling they adopt for a two-layer network. And then there's also this kind of NTK, neural tangent kernel analysis, which uses, which only use order 1 kind of initialization for this beta 1 and beta 2, but use a square root m for this alpha. And also for the mean field, they use m. And also V9E uses a kind of tiny different kind of setups. And they also do some analysis. And we can also like analyze how the scaling regarding this width m. And now we can see that all these different kind of setups are related to the different kind of scalings. And then we try to say, okay, since in all this analysis and practice, there are 3 different kind of hyperparameters, are they really like 3 dimensions of 3 degrees of freedom in determining the training trajectory? The answer is no. There's actually, after normalization, the normalization is, the key normalization is regarding the time. We don't care about time because we only care about the trajectory throughout the training. We only ask, okay, at infinite time, what kind of solution you learn. Therefore, as long as the 2 different models, therefore, after all this renormalization, we can identify that only 2 degrees of freedom there are for these 3 different factors, 3 different hyperparameters. And then what we choose is we choose this beta 1 times beta 2 divided by alpha as our first factor, and this beta 1 divided beta 2 as our second factor. And only these 2 are kind of enough to determine the training trajectory at the infinite width limit from this regate. Oh, here it's simple because there's, for example, there's this we call expansion trick, where you expand this input to x and 1. And then there's a unified approach. That's a convenient trick. Okay, and then, so what's the meaning of this kappa? You can see if you try to ask what is a kind of scale of each neuron at the initialization. You can see the scale is the standard deviation of A, which is beta 1, and the amplitude of this W, which is beta 2, and then there's this alpha coefficient. So each neuron, the scale of each neuron is beta 1 times beta 2 divided by alpha. So that is the meaning of this kappa. And then what is kappa prime? It tells you like how this first layer is different from the second layer. So we call this WK the parameters of the first layer, and this AK as the parameter of the second layer. So this beta 1 over beta 2 tells you the kind of heterogeneity among different layers. Okay, but since we take the infinite width limit, all that important is not the kind of value of kappa, is how kappa changes as the width goes to infinity. Therefore, the key is to extract this kind of power law exponent gamma, where what we use is take this log kappa divided by log m to extract this kind of scaling, the power law scaling coefficient. And then this gamma prime is also the scaling coefficient regarding this kappa. Oh, these 2 equations. You mean these 2 or these 2? Oh, this AK and WK. You mean how to get their? Oh, that is a gradient flow. Regarding the empirical, you can see. Yeah, that's exactly the loss. That is a chain rule. Yeah, and there's nothing more. Yeah. So that's just the normalized gradient flow. And then we try to answer how this gamma and the gamma prime gives you different dynamical behavior at the limit. Okay, so later I will show you a phase diagram, but just to give you a little bit sense about what is a phase diagram. For example, we consider a phase diagram for the water, for this kind of ice, for this kind of transition. So this phase diagram, you may know that the x-axis is the temperature and the y-axis is the pressure, right? Depending on the temperature and the pressure, these molecules or matters can behave in a kind of gas state or liquid state or solid state. And there's a sharp transition between different phases. And this phase diagram is about distinctive state of matter versus this kind of environment, the key factors in the environment. However, what I must tell you from the statistical physics that this sharp transition between different phases only happens at the thermodynamic limit, means that whenever, for example, I only have one molecule of H2O, right? Is there any kind of different phases? No, right? What about 2? What about 3? No. In which sense, there will be this kind of phases. So in statistical physics, we have a characterization that we must take the limit as the size of system or the number of molecules goes to infinity. And there's a sharp transition between different phases characterized by certain discontinuity in terms of their certain properties. Okay, so that is this phase diagram. We only expect sharp transition at the infinite kind of molecule limit, called thermodynamic limit. Okay, and then if we try to obtain a phase diagram for the dynamical region of two-layer neural networks, first we have this something that is similar to the thermodynamic limit, that is the width m goes to infinity. Otherwise, like 1 neuron, 2 neuron, you may not. And then, so we try to say, okay, we have some hyperparameters, for example, gamma and gamma prime, that is like pressure and temperature. And then, depending on these things, gamma and gamma prime, and we may observe different training dynamics. Okay, so, but it's easy to say that them being done initially, so there's, we try to have some kind of criteria to identify what are the things like pressure and temperature in this system. Yeah, so we have some criteria, but later you will see it is gamma and gamma prime, I've told you. Then, so if this gamma is large, that means a smaller initialization. So this is m to the kappa looks like m to the minus gamma. Therefore, when gamma is larger, that means the amplitude decays much faster as m goes to infinity. So large gamma means small initialization, and small gamma means large initialization. So that is how the gamma prime, if it is 0, that means they are balanced initialization between these two layers. And then now, let's just directly look at this phase diagram. First, you can see I kind of marked different points, which are the kind of scaling in this existing method choose. So, and you can see like different kind of points here. And then the meaning of this color, for example, this green area is, we call it condensed regime. So you can see there's no existing point in this condensed region. And there are lots of points on this light blue region. We call this region the linear region. So, and before our work, so all these kind of different places, there are existing work that tells you, okay, there's a lazy training behavior. And at limit, so the dynamics can be linearized. So there's already proofs on these existing lines. But our work kind of unify all these kind of setups and tells you, okay, wherever you are, so in this light blue region, you are in a linear region where at the infinite width limit, it can be approximated by a kernel method. Okay. And in between, there's a sharp transition, right? There's a point at this transition that is the mean field limit. At the mean field limit, so people also, if we observe that there's a certain level of condensation, but not as strong as I present to you. Okay, but this green area is something that you have, no one have actually noticed before our work. So there's no point there, no analysis in this region. And there's a huge, very strong nonlinearity happens in this region. That is the result. Okay, and so still, I will show you the phenomenon, what we can observe in these different regimes. First of all, I will tell you in this linear regime, what happens is that the initialization is relatively like at a larger scale. It's a large initialization. First, in this kind of initialization regime, there's something tricky. It's easy to overfit these points, right? But I kind of say, okay, can we just kind of remove this trivial kind of overfitting that is adopted from the initial output function? Therefore, for all these experiments I do in this linear region, which have large initialization, I always adopt the kind of this anti-symmetrical initialization trick. Therefore, I kind of, when I observe the phenomenon, it's not comes from the trivial kind of way of overfitting. That is from the initial output. Therefore, what you observe is that actually it's not so bad, right? But still, there's a little bit of this kind of thing because you can see the initial, the x-axis is kind of the orientation as you see. The y-axis is amplitude. And these cyan dots marks the location of these neurons at the initialization. And the red dots mark their position at the end of the training. And you can see that they almost does not move or only move a little bit. That is what happened in this linear regime where you use, for example, gamma equals to 0.5 and the gamma prime you just fix to 0. And that is the interpolation behavior you see. And that is what you observe in the parameter space. Okay. It's not so bad. It's still lower frequency dominated fitting, right? As I know from the frequency principle. However, it's just not something you quite like, right? There's neurons almost everywhere. And what happened in the critical regime, where it's in the mean field limit, the gamma equals to 1, and then you can certainly see there's a group of neurons like grow up. However, they are not kind of so concentrated at these two directions. There's a mild level of concentration in this mean field regime. And there's also a condensed regime, so where you can see that these two, the neurons later grow up or aligned at these two directions, marking these two kind of transition points. And now, from this figure, you can understand why this mean field PD is so difficult to analyze. It is because it is under transition. And we all know that if we ask you to understand these crystals of the ice, it's probably there we have effective model. And water, we also have good kind of equations that tell you the laws there. But what about the transition? How the water kind of transition? That is the most complicated part. There's lots of multi-scale phenomena that could happen that makes it so difficult. But you can see this mean field PD is derived in this region. And in this region, the phenomena you observe that there's a certain level of condensation, but still not so exact. Yeah, so it has very rich behavior. Therefore, at that time, I know that we shouldn't really start to look at the nonlinearity from that mean field PD because the mean field behavior is so complicated. So where should we start? Definitely, we should start from this condensed region. Though the nonlinearity is much stronger, however, there's a very kind of clear kind of patterns throughout the training. That is a condensation. And in the regime identification, what we actually do is it's not like we first have some quantities that mark the strength of condensation, because actually condensation is a phenomenon with complexity. But actually we focus on in which regime we got nonlinear behavior. So first of all, let's ask the following question. In which kind of situation a system will behave linearly? So behave linearly means we can approximate these, the whole training dynamics of the nonlinear neural network model by its linear counterpart. Where does this linear counterpart come from? It comes from these kind of tangent functions where you take partial derivatives at the initial point. And then, so you use this tangent function as a basis function. And then you set some coefficients there, right? So therefore, so the whole model is a linearization of the neural network around initialization. So this is a linear counterpart. And the linearity, the linear regime is a regime where the difference between the evolution of this linear model is almost the same as the evolution of the neural network throughout the training. So that is the idea of the linear regime. So what's the key to arrive at a linear regime? First of all, if both AK and WK move so tiny, and then definitely you see that this linear, we can linearize the whole dynamics around initialization. But also, if we consider that AK and WK can behave differently, which one is kind of key to the nonlinearity? Actually, you can see that this W is the key. So if we fix W, right, and then AK moves a lot, you can see it's still a linear model, right? No matter how far A moves, if this W almost does not change, it's still a linear basis model. This W gives you the nonlinear basis, and the A are just a coefficient. Therefore, the magnitude of A does not really matter. All that matters is the magnitude of change throughout the training of this WK. It tells you if all this WK almost does not change, then the whole system can be effectively linearized. Right? That's a key. Therefore, the key quantity to understand is this relative distance of the W. Okay, if the W does not change much compared to its initial value, and then you are sure that you are allowed to linearize these dynamics. Okay, but why we use this relative distance, not the exact distance? Anyone has any idea? So we don't just directly take this 2 norm of this W. We take the relative distance. Actually, I've kind of reviewed a paper where it tells you, okay, as long as this W is close to this initialization in terms of 2 norm, then we can linearize. Actually, that's wrong. The reason is, I've told you that if we set everything to 0, that gives you a saddle point. Around a saddle point, the linear approximation does not work, right? Around that point, what is effective is a second order term, right? The linear approximation is not really effective around 0. Therefore, if your W, even though your W goes tiny bit, but if W itself, W0, is very close to 0, then you perturb it a little bit so that it can cross the 0. Then what's effective is not the first order term, it's the second order term. Yeah. And that's the key. But you see that lots of works in this area are not so careful, so that though they write down a paper, but they waste their time on these kind of obvious mistakes. Yeah. So, but it's easy to make because you don't have a good understanding of that. For example, you don't know that when everything is around 0, there's a saddle point there. Then it's very easy to make these mistakes. You say, okay, L2 is small, then we can linearize, right? Actually, that's not right. Okay, and then now what we should prove is that, okay, in certain regime, for example, in certain linear regime, if we can prove that the relative distance, if we take the soup from 0 to infinity, that goes to 0 at the infinite width limit, and then definitely we can linearize the system. Right? And in the condensed regime, so actually we do not quantify the condensation, but we can prove that the relative distance will go to infinity. That means no way you can use linearization around the initialization to understand the whole dynamics. There's no hope. And in between the critical regime, it's actually very difficult to prove something because it's highly complicated. But also we observe in practice, it's kind of order 1. But it can also have different behavior depending on some like more fine results. And then now, so let's give you some, we call this scaling analysis. This scaling analysis is not mathematically rigorous. However, just from this scaling analysis, you are able to know where these critical lines happens, right? But this is not the rigorous mathematical proof, but I found it's quite effective because it's kind of intuitive shortcut to this whole phase diagram. I think physicists are actually very good at it, right? They usually already plot this phase diagram, which are effective before we can actually prove there's a phase transition happen there, right? And therefore, I also put this kind of intuitive scaling analysis. How to understand that? Because all we care is whether this W change, change much or not. So the question is, like, why we don't need this W to change much, right? In which sense this W or must change a lot. So let's recall the physical meaning of this kappa. This kappa is the amplitude of each neuron at initialization. That is a rough scale of each neuron. And this kappa prime is kind of the difference between these alpha and WK. And then if we look at the capability of neural network, we see that, okay, each neuron has a magnitude of beta 1, beta 2 divided by alpha, right? And then if I'm allowed to just sum them up, it's not like, I want to say is that what is the kind of a maximum kind of a magnitude it can express? Okay, therefore I just put this m. But if it is, we really think they are stochastic, we should put like square root m, right? But we are thinking about whether if I allow them to kind of express in its maximum capacity, what is kind of amplitude it can express? And then I just put this m, because they can kind of align, right, to contribute this m factor. It's just like mean field limit. Therefore, this m kappa is actually the capacity of the network at the initialization. It means any kind of target that is much larger than this m kappa, it must go away, go further away to express that. Okay, if it is within this m kappa, then that means probably you are allowed to not change so much. Okay, and then we will know that if this kappa is greater or equal to this 1 over m, and then we know that initially it could have enough capacity to express any kind of order 1 output or over order 1 training samples. And then that gives us this line, this critical. It tells you why 1 over m is actually critical. So here, this is this gamma equals to 1 means it's a 1 over m scaling. And then if this kappa is greater or equal to 1 over m, then it means it is allowed to not to move much in order to fit the training data. And then there's another line, which is kind of the diagonal line. The diagonal comes from the following argument. It's about whether the output layer could dominate or not. Okay, so it says that if the kind of output layer, we could measure its kind of contribution. And then if the output layer is kind of much faster than this kind of input layer, this WK, then, or this WK is just trained so slow, right, compared to this output AK. The kind of, evolves at a much slower rate. And then this AK will dominate the training. And then the AK, because we know that an infinite width limit, the random basis is already able to kind of interpolate everything. Therefore, because A is so fast, then the evolution of A dominates everything. And then that is the estimate you can do regarding this part, and you get this diagonal line in the phase diagram. Okay, so that is roughly, there's a kind of scaling analysis that tells you why transition happened in that places. Also, you can do experiment. What you can do is that you, as m goes to infinity, you can measure the relative distance, right? The relative distance as the m become larger and larger. And using different gamma, you can observe the change of this relative distance. And then you can kind of extrapolate. And you can see, indeed, like when gamma equals to 1 at the transition, like it's the flat line, right? It's like order 1. Okay. And we can also empirically observe like when in the phase diagram this relative distance goes to 0, when it goes to infinity. So that is, in that sense, we obtain this empirical phase diagram. You can see this empirical phase diagram on the synthetic data or the MNIST data is actually quite well aligned with this, the theoretical transition line. Therefore, so whenever we really dive into the theory, we always first do this very careful kind of a numerical experiment. So if it really aligns with all our expectations, and then we know that it's likely we are going to prove these theories. And then let me tell you, okay, where the name of condensation comes from. What we can show is that in this condensed regime, that the relative distance of W goes to infinity, right? It goes too far away so that there's a strong nonlinearity there. But what is a feature that marks this nonlinear regime? What we can observe is that the x-axis is also like the feature, is the angles. And then as we increase the width of network, you can see in this condensed regime, the kind of support of these neuron groups become more and more concentrated, right, at the final training. And that is, you can see from the blue to red to yellow, which is a 10 to the 6, it's a million neurons, right? You can see clearly this kind of tendency. Therefore, because we observe this very clear pattern, we name this regime as a condensed regime, right? Okay. And in this graph, you can also see in this kind of in this transition regime. So its behavior is indeed kind of more complicated. There's also like more realistic data, MNIST. This experiment is more difficult, but still you can see or you can feel the similar tendency as you increase the width of network, the condensation becomes stronger and stronger. But definitely, okay, you are not going to get this such clean result as we use the synthetic data. Therefore, without understanding from the very simple setups, if I give you this result, you observe nothing, right? Very clear understanding with the simple setups. Now you know it's aligned with the results we see in simple setups. Okay, so and then later we prove the theorems rigorously in terms of mathematics that, okay, in this light blue regime, the relative distance goes to 0, and in this blue regime, it goes to infinity. And then that solves the criticality of this blue line. However, we are not able to prove that it converges to order 1 in this critical regime. And now it's a phase diagram we see. And as I've told you, what we are really interested in beyond the linearity, because at that time, like 2020, everything about this part is already known. There's no more we should further look into. And however, all this regime, like this like this green regime and this critical regime marked by blue line, is not known. Yeah. And then, which part should we look first? Definitely this green regime, not this transition regime. That's why later we really only focus on the situation where we use very small initialization and to see strong condensation. It's not because this strong condensation situation is really practical. Actually, I would argue this mean field regime is more practical because generally we do need some level of condensation, right? But not necessarily to an extent or to an extreme level. But it is only at the extreme level we see very clear patterns that allow us to kind of understand these nonlinear training dynamics better. Okay, that is for the simplicity of the understanding. Okay, and I would say in 2020, I already know that anyone that tries to understand this mean field dynamics or mean field PDE, our understanding of this mean field PDE almost stuck. There's no much. 20. Therefore, so you see that there's too many traps you could encounter when you try to understand this system. Just stick to that PD, 5 years, you don't get anything. Okay. And later, we did something in the 3-layer ReLU network. So there's no theorems, because in 3 layers, proving theorems is more difficult. But still, as we can see, we can use empirical method, right? Like this empirical phase diagram. What we do is like this before. We use some relative distance, and then we see how this relative distance throughout the training changes as we increase the width of the network. That is how we do. And we mark the slope to tell us to extrapolate to get whether it goes to infinity or goes to 0. And it is with this method that we obtain this 3-layer phase diagram. And what's new in this 3-layer phase diagram? First of all, actually there are like 3 effective things. Like actually there's like gamma 1, gamma 2, and gamma 3. Here, I think we only focus on this gamma 2 and the gamma 3, and we fix the other one. Because otherwise, the phase diagram will become 3-dimensional, right? It's very difficult to visualize. Therefore, we kind of fix certain parameter, and then only change the other 2 hyperparameters. And then this is the phase diagram we get. So what we learn from that, okay, in this region, still there's a kind of a linear region where everything is like kernel method. And there's this kind of purple regime where both the first hidden layer and second hidden layer condenses. Means the relative distance will go to infinity. And then in this green region or in this blue region, only one layer condenses, the other does not change. And therefore, depending on the scale of initialization, you can tune the network such that only like the first hidden layer evolves a lot, or only first layer condense, but second layer does not, or the opposite, right? Or both of them condense, right? And now with all these understandings, you have a much better understanding of what are the consequences when you tune different layers with different variance, right? Okay, there's a kind of when you tune to a smaller value, there's a stronger condensation. A larger value, there's a less. You have this kind of understanding, okay? And the last part of this talk, so I will tell you a little story about condensation facilitated reasoning, because all of you, it's now all about large language models, right? And we know that, okay, there's a transformer, we can tune the network so that it can condense more or condense less, right? What's the benefit of the condensation, right? For example, for the ability like reasoning ability. Okay, here's this little story. Actually, the major contributor is my collaborator, Zhang, who actually devised this kind of nice synthetic platform that is called this anchor function platform, which is a kind of a synthetic language-like task, but with very clear kind of patterns. Okay, so these are the training samples we have. Yeah, so all I give to a transformer is that these kind of training inputs and there's certain kind of target. So what's the rule underlying this training data? So what we do is like these 1 and 4, we call it anchors. So these anchors are actually 1 marks special operation is +5, and 2 marks operation of +1, and 3 and 4 marks -2 and -8. And we do these operations on which on which number? That is a number before this 1, 1, 2, 4, right? Therefore, this 28, it's these 2 of the 1, then it gives you like a +10. Therefore, the target is 38. That rule is the rule we use to generate all this training data. But the network do not know that. What it says is all this training data, right? I give them the training data. And then what we do is like, okay, I have a compositional rule where we have 1, 2, 1, 1, 1, 2, or 4, 4. There's 16 different type of kind of operations that could happen to this kind of prior kind of token. And then we can ask the following question. So if for the 3 and 4, you can see 3, if we have 3 and 4, it should be like -10, right? However, if I change the rule for 3 and 4 to -6 in our training data, and then I ask how the neural network will infer on the 4-3. Yeah. Initially, the 4-3 is like -10, right? And then if I ask you, okay, so what is the 4-3? If this 3-4 is very good, it's like, for example, -10. Then you think, oh, giving this like 15 different kind of training data, the network may be able to identify, okay, these patterns, or just based on 3-4, based on symmetry rule, it assigns the value of operation of 3-4 to 4-3, right? There are two kind of possibilities. One is learn the composition rule and learn that 1 means +5 and 2 means +1. And the other is that since you see there's a symmetry there, right? 1-2 is the same as 2-1. Then it can assign the operation it learned from 3-4 and assign that operation to this 4-3. And then what is your guess? That is the training data. I give them like these 15 different kind of training data. There's this 15 kind of different anchors it sees. How it predict on this 4-3? -10 or -6? -6, right? Anyone think it should be -10? There's -10. Yeah. And the -10 comes from realizing there's 4 basic units, right? For basic operations. And I can tell you that depending on the initialization, different things can happen. Okay. And there are two kind of mechanisms, right? First is a symmetry mechanism. If it learns based on symmetry, then it's -6. Then if it learns based on composition, then it should predict -10. And then, so here's a kind of regime where we set -6 as the correct answer, as a target, as a correct answer. And then this axis is this initialization scale, gamma. So this is like the D input is a dimension of, is a width of that layer. So it's to the gamma. So the gamma, if it becomes larger, that means smaller initialization. If it's larger, that means larger initialization. And in this regime, a little bit less than 0.5, and you can see it's highly correct. Aligned with this -6 because you use -6 as a correct answer. And it's highly accurate. However, if you use -10 as a correct answer, then you see that's the regime, right? It's with a smaller initialization, and then you see very kind of close to 1 kind of accurate. That means if you initialize a network with very small initialization, it predicts wrong. But however, what I can tell you is that this kind of task is highly out of distribution because the network never sees 4-3, right? Never seen. But it's the only thing it has is some existing kind of. And then, depending on initialization, right, it can learn kind of different results. Which result is actually you think is better? What kind of answer do you want the neural network to learn? -10 or -6? I think -10, right? Because it's a kind of simpler explanation of all these existing data, right? And then you can see if you use small initialization, the network will condense more strongly. So that is what you see. If you use small initialization, you observe this, cosine similarity matrix of this query or other matrix. You can see very strong condensation happen. And then it is in this kind of pattern, it predicts -10. However, if you have a very large initialization, there's a very mild or a very kind of minimal level of condensation. And therefore, it is not able to really learn the minimal complexity explanation. Actually, here, in the training data, there's no error. Oh, you mean this -6 as a certain kind of error, right? Yeah, so actually, that happens if you use very small initialization, then you force the network to condense more, right? Condense means the effective complexity of the network is actually smaller. You force the network to use a minimal complexity state to explain all the training data, right? That is what you force the network to do. And then it captures the composition pattern, because that's a kind of a lower complexity. And then that is an intermediate state you can observe. I can say, without the understanding of condensation, you don't know what kind of things you want to observe. But there's a very clear pattern. And all of these understandings are aligned with what we observe in very simple setup, like two-layer. And yeah, and there's a basic understanding why this kind of symmetry is more complicated and why this is a kind of a simpler. It's because here, the composition, you only need to learn 4 functions, and then everything else is composition. But here, you need to learn 10 different things, and then you can use symmetry to infer the other 6. Yeah, so it's different complexity. Okay, and let's go a little bit deeper. So what happens in this embedding space, what kind of embedding it learns, you can see that with strong condensation, these kind of embedding of this number are highly organized. Right? That is what we see. And however, with large initialization, there's hardly any pattern you can. Therefore, why you should expect very strong, this kind of, we call order of distribution generalization. So for example, if you know that for 42, so you should learn something that help it move along that direction towards 45, that is +3, right? Then, even though it may not exactly see 35, but if you learn the same kind of perturbation, you know that certain operation is just towards that direction. And then you decode that, it's +3, right? This kind of organization is always highly kind of valuable for order of distribution generalization. Really learn this kind of pattern. Okay, and there's a further thing we can see, if it predicts, for example, -6, right? It learns some symmetry. You can look at the information flow. You can see that first it combines 4 and 3 to one node. And then, based on this combination of 4 and 3, it do some operation on this 99 and get 93. First, combine these 2 anchors. However, if in another type where you see -10, it use composition, right? And then you can see this node, the 4 node, do something on this 99. It attends to a 99, do something. And then this 3, also kind of do something on this kind of, on this node to get like 89. So there's a kind of two steps, not just to combine these 2 anchors and then give one answer, right? There are different patterns you can observe. And then that's the kind of the general thing you could expect. That is like with small initialization, you see very strong condensation. So the network try to explain the data as low complexity as possible. Therefore, it only learns 4 anchors. That gives them very strong capability of However, with very large initialization, actually, I didn't mention there's a very large initialization. There's no condense at all. Therefore, it almost does not generalize even within the distribution. That means, so even you see lots of, like, for example, +3 on these even numbers, it does not generalize to odd numbers. But you see the same, for example, 1, 3. But you only give all this data on the even numbers, but it does not generalize on the odd numbers, right? And there's certain pattern. And today, what I talk about is these 2 parts. I talk about the phase diagram, about the regime of the condensation, and talk a little bit about this, the impact of this initialization impact on the kind of reasoning part, right? And tomorrow and the day after tomorrow, I will talk about, for example, the landscape aspects of the condensation, and also how to understand the generalization benefit. All these works you can find on my personal website. And, yeah, there's a little bit of problems. If you can answer them, you really understand these things better. Okay, and I will stop here today.